Good morning to everyone, dear students. Today we are having the revision class. The topic is you are observing the main heading as electric potential and capacitors, means capacitances, in which first we will have the definition here. Electric potential. Now, what is the electric potential definition? Means electric potential is nothing but work, some amount of work. Means the amount of work done by an external force in bringing a unit positive charge from infinity to a given point in the electric field against the direction of field is called electric potential. In bracket they have shown electric potential is denoted by V, capital V. See, mathematically how to write the electric potential means, okay, V is equal to W by Q. That means electric potential is equal to W means work done, Q means charge. Work done by charge is nothing but here electric potential. Right, what is the unit of electric potential? Means unit of electric potential, SI unit of electric potential is volt. Otherwise you can write in MKS system joule per coulomb, joule coulomb inverse also. 1 joule coulomb inverse is equal to 1 volt. Right, let me see here what is the definition of 1 volt. Definition of 1 volt is, see, you are observing in the formula. Okay, V is equal to 1 volt. Volt potential is equal to 1 volt. When the potential is said to be 1 volt means, suppose 1 joule of work has to be done in moving 1 coulomb of charge from infinity to the point against the field is called 1 volt. Is it? That means 1 joule of work you have done to bringing 1 coulomb of charge from infinity to a given point in the electric field, of course against the direction of electric field means, then that work done is said to be here 1 volt. That means that potential is said to be here 1 volt. After 1 volt, you see here electric potential difference. Potential difference. What is the difference between these two? Let me see here. Potential means amount of work done to bring a unit positive charge from infinity to a point in the electric field against the direction of field. Electric potential means it is defined as the amount of work done by external force in moving unit positive charge between 2 points in the field. That means inside the electric field from one point to another point, if you suppose move a unit positive charge means you must do some work. That work you are doing inside the electric field itself only. Is it? So, to show the difference in the position of the charged particle, that means to move the charged particle from one point to another point in the electric field is called here electric potential difference. From infinity to a point, given point in the electric field means, then that is said to be here electric field, electric potential. Inside the electric field from one point to another point, suppose if you want to move the charged particle means that is said to be electric potential difference. Yes, right, suppose from point to R to point P if you want to move the charged particle means, so P to R to P you are changing the position of the charged particle in the electric field. That's why there the potential difference we can write like this. So after having this, we are having one 5-mark question. Let me see here. Expression for electric potential due to a point charge. You are observing in the diagram, in extreme left, R is in, point O is there. At that point, there is a positive charge. That positive charge is capital Q. Is it? Capital Q. Right. Now from capital Q charge at a distance R, see there is one point is there. That point is said to be here P point. Is it? In extreme right, at the end of the diagram, there is infinity point is there. Now you just see here, from infinity distance to 1 coulomb of charge, suppose if you are bringing one of the point P dash as shown in figure, that point P dash is at a distance R dash from capital Q charge. Is it? For Q is greater than 0, that means Q is greater than 0 means charge is positive, potential also greater than 0. So here one of the charged particle plus C plus 1C, 1 means unit means 1 coulomb. 1 coulomb of charge they have brought from infinity to a point P as shown in figure. In that case, here capital Q charge is there, here plus 1 Q charge is there. Okay, these two are initially at a distance R dash. In that case, in between these two, okay, electrostatic repulsive force will be exist. That electrostatic repulsive force is nothing but here F is equal to 1 by 4 pi epsilon naught. We are having F equal to 1 by 4 pi epsilon naught capital Q1 Q2 divided by R square. But here 1 by 4 pi epsilon naught, Q1 means capital Q, Q2 means 1 coulomb divided by R square means R dash square. We can take, that is equation number 1. Right, where R cap dash is nothing but unit vector along the direction. Unit vector, that is unit vector of force. Right. Next to work done to move the charge from R dash to R dash point P dash to any one of the intermediate point, that is nothing but delta R dash position. Now in that case, work done is equal to what we can write means, basically we know that work done can be defined as the dot product of force and displacement. So for a small displacement, small work done, delta W equal to, we can write F bar dot delta R bar dash. From this one, 1 by 4 pi epsilon naught Q divided by, okay, force means force equation 1 in force is there. That force value completely you substitute, okay, instead of F bar, and delta R bar as it is you write. And actually delta F bar by F bar by delta R bar means dot product F delta R cos theta we can write. But here displacement and force both are in opposite direction. That's why cos theta is nothing but cos 180. Cos 180 value is minus 1. So minus 1 value minus you have written in the beginning of the equation itself only. So minus 1 by 4 by epsilon naught Q divided by delta R dash divided by Q divided by R dash square into delta R dash we can write. That is equation number 1. The delta negative signs shows that delta R dash is lesser than 0. Okay, let it be. The total work done to bring the unit positive charge from infinity to point P in the diagram. See, from infinity to bring the unit positive charge point P in the electric field. So total work done means we have to make it integration from where to where? From infinity to r distance. So from this one, work done is equal to total work done capital W equal to minus of integral infinity to r 1 by 4 pi epsilon naught q divided by r dash square into delta r we can write, dr we can write. Now from this one, on integration them, what we may get means last in the end of the equation 1 by 4 pi epsilon naught q divided by r we may get. Now this work done is equal to the potential, that's why last equation v equal to 1 by 4 pi epsilon naught capital Q by r is nothing but electric potential. That is, you just see electric potential due to a point charge is nothing but we can write 1 by 4 pi epsilon naught q divided by r. But whereas you see electric field is 1 by 4 pi epsilon naught q divided by r square, already we have studied in first chapter. Here electric potential 1 by 4 pi epsilon naught q divided by r we got. For q less than 0, v less than 0, in that case work done will be negative. If the charge is positive, potential is positive. Charge is negative means potential also negative. Afterwards, whether you are observing or not, there is one graph as given in the diagram. That graph is nothing but, see the heading, variation of electric field and electric potential with the distance from point charge. See, an equation from the equation, E is proportional to the square of the distance. Electric potential V is inversely proportional to distance. So, in case of electric field, the variation of electric field is inversely square. But in case of potential, the variation of the distance is inversely but not square. So if you see the diagram, electric field is mentioned with the dotted lines in graph. Electric potential is mentioned with this solid line. You are observing or not, on y-axis they have taken electric field and potential. On x-axis they have taken distance. Since electric field is inversely proportional to the square of the distance, because of that rapidly electric field is decreases with the distance. But electric potential is, it won't decreases like this. So you just observe. Okay, electric field you have to show rapidly. Okay, like this, right? After having this expression for electric potential due to electric dipole, right? Here you are observing in the diagram, it is the electric dipole clearly. This is the electric dipole. In this electric dipole, see, bottom to top I am going to explain. Okay, here first there is one negative charge is there in down. There is a positive charge is there up at up, right? Suppose if the two charges are separated by a distance is nothing but 2a we can take. So electric dipole is an arrangement, is it? So in which two charges equal in magnitude, opposite in sign, are separated by a small distance 2a means that arrangement is said to be here electric dipole. Now due to this electric dipole at a distance r, you are observing in the diagram, at a distance r, see at a distance r, okay, at a point P, you have to find out the electric potential. Now you have to find out the electric potential means, first of all you see there are two charges are there, plus q charge. Due to plus q charge electric potential, due to minus q charge potential we have to take first. So due to plus q charge that is 1 by 4 pi epsilon naught q divided by r1. Why? Because from plus q, the point P is at a distance r1. Due to minus q, the charge is, the electric potential is 1 by 4 pi epsilon naught minus q divided by r2. Why? Because from minus q charge, point P is at a distance r2. Now you are observing or not here, the total potential means, you see, the total potential due to dipole at a point P is given by V equal to, we can write, actually that step has not given in the material, V is equal to, we can write V plus Q plus V minus Q. So total potential V is equal to 1 by 4 pi epsilon naught is common, Q also common, Q divided by R1 minus Q divided by R2, where R1 and R2 are distances of point P from plus Q and minus Q. Already I have shown in the diagram. Now by the geometry means I have explained this one in your video class. You just see, R1 square means you take R square plus A square minus 2RA cos theta. R2 square means R square plus A square plus 2AR cos theta. In both, the difference thing is nothing but only 1. For R1, 1 minus will come. For R2, all are pluses only. So if you come to the point of R1 square equal to, okay, first R1 square is there, in which if you take R common, you may get 1 plus A square by R square minus 2A cos theta by R. Somewhat differently they have written, no problem. But compared to the R square, compared to the, here in the diagram you see, R is very lengthy line. In the figure, from Q to O you see that is A. From O to minus Q you see that is distance is nothing but A. So compared to the R, A is very small. That's why compared to the R square, A square is very small. That's why A square value can be neglected. After neglecting A square, you may get R1 square is approximately equal to R square bracket begin 1 minus 2A cos theta by R. Okay, right. In similar way, R2 square means how we can write? R square into 1 plus. See, R1 means 1 minus. R2 means 1 plus you may get. Right, 1 plus 2A cos theta by R. Right, from the binomial theorem. By using the binomial theorem, see first R1, okay, R1 square is there here. R1 square I have converted into the R. R is equal to what I can write means R1 is equal to R1 square equal to R square into 1 minus 2A cos theta by R is there. If it convert into the R equal to, if it convert into the R1 is approximately equal to R into 1 minus 2 cos theta by R whole power 1 by 2 you may get. And removing the square, for 1 minus 2A cos theta by R you may get whole power 1 by 2. See here. If you make it reciprocal, so 1 by R1 equal to 1 by R into 1 minus 2A cos theta by R whole power minus half, that equal to, after application of binomial theorem, 1 by R1 equal to, see at the end of the equation, first equation only, approximately equal to 1 by R into 1 plus A cos theta by R. In similar way, 1 by R2 equal to 1 by R into 1 minus A by R cos theta you may get. Is it? Right. Now this 1 by R1 and 1 by R2, whatever we got, those two we have to substitute in this given equation. See, there is a given equation, one of the equation number 1 is there, V equal to 1 by Q by 4 pi epsilon naught, 1 by R1 minus 1 by R2. If you substitute here, you may get V is equal to 1 by 4 pi epsilon naught Q into 2a cos theta by R square. But Q into 2a is equal to the dipole moment, that is P. So last time I got here 1 by 4 pi epsilon naught P cos theta by R square. P cos theta, how we can write? P bar dot R bar also we can write. So V equal to 1 by 4 pi epsilon naught P bar dot R bar R square also we can write. Okay. Now this is nothing but here electric potential due to the dipole. Till here you have to write. But no need of special cases here. Special cases are only for understanding purpose to improve the subject itself. So you are observing here comparison of electric potential at a point due to electric dipole and a point charge. See, due to dipole, electric potential is varies inversely proportional to square of the distance. Due to point charge, electric potential varies inversely proportional to only distance. Is it? So you just remember this one also. Afterwards, electric potential due to system of charges is there. Consider the system of charges Q1, Q2 and so on Q1 with the position vectors R1, R2 and so on R1. That means due to multiple charges, due to the system of charges, what is the electric potential at a particular point means we have to write. See here they have given. See in the diagram they have given Q1, Q2, Q3, Q4, Q5 and so on charges are there. Of course they are being at their respective positions. Right, from their respective positions at a point P you have to calculate electric potential. In that case, how to write the electric potential means due to Q1 charge first of all. Due to Q1 charge, electric potential at point P is nothing but 1 by 4 pi epsilon naught Q1 divided by, we can write R1. In similar way, due to second charge, 1 by 4 pi epsilon naught Q2 divided by R2P. Due to third charge, 1 by 4 pi epsilon naught Q3 divided by R3. Like that. Right, by the superposition principle, electric potential at point P due to the all charges is nothing but algebraic sum of potential due to individual charges. So total charge at point P V equal to V1 plus V2 plus V3 plus and so on plus Vn we can write. So from this one if you take common thing 1 by 4 pi epsilon naught. So you may write here 1 by Q1 by R1 plus Q2 by R2 plus and so on plus Q1 by R. That is if you write in summation form 1 by 4 pi epsilon naught summation I is equal to 1 to N Qi by Ri we can write. Now this is said to be here electric potential due to the system of charges. Is it? Now dear students, you just observe here. Okay, few of the concepts I have explained in this video. In further next video I will explain remaining things. Yes, right. Still I am continuing here equipotential surfaces. Equipotential surface means you just remember only one thing. The surface on which electric potential is constant at any point. That surface is said to be here equipotential surface. Right. In case of a unit charge, single charge, equipotential surfaces shape is spherical we can take. Right, in different cases I have given. Okay, right. Related to these equipotential surfaces, some of the points are given 1, 2, 3 you see. for any charge configuration, equipotential surface through a point is normal to the electric field at that point. That means at any point if you choose an equipotential surface, at that point if you wanted to write, if you wanted to draw the electric field, means that electric field line direction is normal to the direction of equipotential surface. Of course, suppose second point, if you see, if any point charge has to move from one point to another point on the equipotential surface, the work done to move from one point to another point, that charge is zero. That means no work is required to move a unit test charge from one point to another point on the equipotential surface. That is, work done is zero. Next, electric field is to be normal to the equipotential at every point. Additionally, one more point I am saying here, point 4, not given here. Two equipotential surfaces, they never intersect with each other. That is also one of the point. Afterwards, for equipotential surfaces they have given for different cases. For a dipole and two identical charges. First, dipole means diagram A, B they have given. In diagram A, dipole is there. In diagram B, two identical charges are there. How to draw the equipotential surfaces? You just observe there. Where the lines are crowded, where the lines are wided. Clearly I have explained in our video class. You just see. Afterwards, if you see here, equipotential surface for uniform electric field, how to draw means like this we have to draw. Plane. Equipotential surface shape is plane for uniform electric field. Right. Thereafter, if you come, very important question, derive the relation between electric field and electric potential. You are observing there are two equipotential surfaces are there. In bottom, A is there, at the top B is there. First, at the top B plane, that is, at bottom plate is nothing but A plate is there. A plate is having throughout on its surface V potential. B surface is having V plus delta V. That means there is a difference between A and B in potentials. Both are not having the same potentials. But when you take individually, both are having same potentials. Is it? Right now, you come to the point of here. If you want to move the unit positive charge from point A to point B through a small distance delta L, okay, then the work done is equal to potential difference. So that potential difference is nothing but, how we can write? Let me see here. E bar dot delta L bar is equal to VA minus VB. We can write VA means V minus of VB means V plus delta V. On simplification, E bar is equal to, we can write delta V bar divided by delta L bar. Sorry, delta V divided by delta L. So minus sign, what it indicates means, minus case is indicates that we have moved the charged particle from one point to another point on the equipotential surface. Is it? Of course, negative sign is there for electric potential, that we have converted by taking the modulus. If you take the ratio of delta V by delta L, means that ratio is also known as potential gradient. Is it? Now this is the relation between electric potential and electric potential difference. I have given very clearly in our class also, ma video class. You just observe that. Remaining things I will continue in our next class. So just to follow the videos.